In this section, we're going to look at the general exponential function. One of the forms is y equals c times a to the t power. Base a is greater than 0, and a is not equal to 1. And c is a constant. It's just a real number. We're going to look at data, and in this part, our data is going to be equally spaced x values. And if that's the case, then the ratio of consecutive y values is constant. So if the input is equally spaced, the output values, when you take the ratios, you get a constant, or nearly constant. In real life, sometimes you have to round to get things to be the same, and so constant generally. So let's look at some data. Let's see, let's take t values, 0, 1, and 2, and let's have some y values, 0.9, 0.75, 0.625. And we want to see if we can actually find an exponential function of this form, y equals c times a to the t, that will represent this data. If we can find that, we can use new values for t, greater than 2, in order to find other output values. So I'm looking for c and a, and I know that if I have equally spaced x, the output value ratios are constant, so let's look at the ratios of the output values. I'm going to take the next y value and divide it by the current y value. So that if I look at the y value that's the next one, it would be 0.75, and I divide it by the first one, or the current one. So that would be 0.75 divided by 0.9. If you do that, you get approximately 0.83333. Now, I'm carrying out a lot of decimal places even though I know that 3 continues, because if you round too soon, your data will not give you correct outputs. And if I also check the next output divided by the current output, I get the same thing. You don't want to round this to 0.8. You don't even want 0.83. You really do want to keep 4 to 6 decimal places at a minimum in all the work that you're doing with these. So this value, this ratio, gives me A. So A is called the growth rate, equals 0.83333. It's called the growth rate because if you think about it, if you take 0.9, multiply it by your A, you'll get 0.75. Because that's how the grows. If you multiply 0.75 times 0.83333, you'll get the next output. So that's how the function grows. So I want to take my A, and now I need to try to find my C value. Well, let's see what I can do with C up here. I know what A is equal to. So let's look at y equals c times a to the t. I have a whole string of y's, a whole string of t's. I think I'm going to use the first one and see what I get for c using t and y and a. My y value is 0.9. I don't know c. My a value is 0.83333. And my t value for this one is 0. Well, this to the 0 power is 1, so c is 0.9. So my formula is actually y equal to 0.9 times 0.83333 raised to the t power. If you want to test it, you can plug in 1 for t and see if you get about this output, or plug in 2 for t to see if you get this output. And if I want to know what I get for the output, if t is equal to 3 or 5 or 7, I can plug that in for t and it will give me y. So this will give us the growth rate and a formula that matches what we're looking for with the base A. We're going to look at a little bit different type of data. We don't have a 0 point here. It's 2 units in between, but you can get a decent formula for a function with just 2 data points. Remember that it's an exponential function, so the ratios of the outputs are constant. So let's first look at the ratios of the outputs. I'll take the next y value and divide by the current y value. So in this case, the next one is 20.25, and the first one is 9. Well, the only problem with that is, what do I do about the 2 numbers in here? I have a 2 and a 4. So instead of just using the y values, we're going to actually use the equation with the y values. If I use y equals c times a to the t and I want the next y value, I use the whole point in the formula. So y is equal to c, I don't know, times a to the 4th. I'm also going to look at the first point. If I put that in, I'll have 9 equal to c times a to the 2nd power. So I've taken both data points and put them in there, and now I'm going to do the ratios of the y's. This y value, 20.25, needs to divide by 9, the way we started before. This is also a representation of the output, so I'm going to take this output and divide by this output. Well, when I do that, the c's cancel. And if I divide 20.25 by 9, I get 2.25 equal to an a to the 4th over a squared. If you remember your rules for exponents, I subtract the exponents and keep the base. I get a squared. Now this is not a. A is the growth rate, the growth factor. We're talking exponential growth or decay. But I can take the square root of both sides, and if I take the square root, I get 1.5 for a. So a is the growth factor, and that is the base that goes in my formula. To try to find the rest of the formula, I don't have c. I canceled it, but look over here. This other formula that I put down here, I already have it written. Let's put a in here, and then my only unknown will be c. So I have 9 equal to c times a squared, which is 2.25. And when I divide, 9 divided by 2.25, I get 4. C is 4. I have my formula. If I'll have y equals c times a to the t, I now have y equal to 4 times 1.5 to the t power. And that's my formula. You can use this with any data that's equally spaced. If this had been 2, 4, 6, 8, I'd use the same method, probably with just these 2 points to see how it works, and then do test points. If I want to know what y is equal to, if t is 6, I'd put in t equal to 6 and find y. Okay? So you can use this anytime the data is equally spaced x values. Lots of different types of formulas are based on the natural exponential function. Right now we're going to look at the standard y equals y sub 0 times e raised to the kt power. Now that will also have lots of different letters that mean the same thing. It could be n equals n sub 0 e to the kt. It could be a equals p e to the rt. Usually the last refers to money, growth, interest rate, principal investment. A lot of times the n refers to the number in a population, and that's what we're going to look at now. We have a city that in 1990 had a population of 100,000. In 1993, the population had dropped to 96,450. And what we want to do now is see if we can find a formula to represent this so that we can estimate the population in 2010. Now, one of the things that we do with data, this is a year. We don't use years in our formula. T is the time since a certain year. It's aligning the data. So I'm going to stick in here T values so that this will be T equal to 0 will represent the year 1990. And so 1993 minus 1990 would be year 3. And this is our output I'll use in for the number of people in the population. And I want to find my formula. If I use n equals n sub 0 e to the kt, with all these formulas, start with the 0 data point. So n, the number is 100,000, equal to n sub 0 e to the k times 0. There are a lot of letters and a lot you don't know. But e to the 0 is 1, so 100,000 is n sub 0, and that means it is now a constant, not just a data point. So we can always assume that the 0 will give us n sub 0, n naught. So the formula that we're working with now is y equals 100,000 e to the kt. And let's use the second data point. I think I'll use my n like I started with. N is now 96,450 equal to 100,000 e to the k times 3. K is my unknown. I need to move everything away from the k. So it's 100,000 times that, so I will divide by 100,000, which would be 5 decimals, which gives me 0.96450, equal to e to the k times 3. Now at this point, to solve for k, I need to use the natural log. So I'll take the natural log of this side equal to the natural log of this side. And then there are a couple ways you have to think of this from here. There's a rule for logarithms that says the k times 3 is a multiplier that can be brought around front. If it's the power of the e, you can write it in front. Or you can remember that the natural log is log base e, and if there's an e next to it, it goes away. So I just end up with k times 3. Either way you think about it, as either k times 3 ln of e, and then the ln of e is actually 1, so you have k times 3, or that log base e of e to some power goes away completely, and you're left with k times 3. Divide by 3 on both sides. We find out that the natural log of 0.96450 divided by 3 is negative 0.012408. Remember, you want to be using 4 to 6 decimal places. Okay, so this is our value for k. Now I can go back up into my formula, put in my value for k, and the t value for my population in 2010. 2010 minus 1990 is 20. So the next t value that I have out here to use is 20. And that will give me the population in 2010. So here's k. I have n equal to 100,000. I run out of room. Keep my k there so I can see it. N equals 100,000. E to the negative 0.012408 times t, and then my t is going to be 20. Multiply those two first. Be sure you make it negative. Use e to the x, enter that number, multiply by 100,000, and you should end up with the population is 78,587. So we call these growth functions, but in this case, it's actually a decay function, and that's because our exponent was negative, so that the population was going down. Things like this are important because of things like federal funding for schools, businesses in depressed areas. Clearly, economics has not been good for the city. Now let's look at rewriting y equals c times a to the t in terms of y equals y sub 0 e to the kt, because these are interchangeable in many cases. Since they're both y, I'll set the right-hand sides of the equations equal to each other. C times a to the t is equal to y sub 0 times e to the kt. Now the c and the y sub 0 are both our constant terms. So let's just look at the a to the t and the e to the kt part. When it's a constant, I could call this c, I could call that y sub 0. The letters don't matter. Here I see a t and there's a t over there. So let's think of this as base a raised to the t power. And over here I can split up the exponent, because one of our rules for exponents says that if you have something raised to a power and then raised to another power, those two exponents multiply. So we're going backwards from that step. So since these are both raised to the t power, a is equal to e to the k. Let's look at an example. Suppose I start off with y equals e raised to the negative 0.09x. And I want to rewrite that in terms of c times a to the t, or just a to the t because there's not a constant in front. So I'm going to split up the exponent and write e to the negative 0.09 and then all that to the x power. If I raise e to the negative 0.09 to get a decimal, what I get is 0.91393 to the x power. So I've taken my form in e and made it to a form in a, where a is 0.91393. Let's look at another example. Y equals 0.33 raised to the power negative 2.2x. Now this is a little different because usually when it's been base a, the exponent has not had a constant in front of it. So I want to first change it to a to the t form. So here also I will take my 0.3 and split up the exponent by putting the 2.2 with the 0.3 and then to the x power. If I take 0.3, raise it to the negative 2.2, I'll get 14.136218, something like that, and then to the x power. So I first had to write this in terms just as a to the x. And now I want to go from this form back to the e form. Let's look back over here for a minute. I know that a is the same as the e to the k. So if you think about when we've used the natural log to solve for a value, let's take the natural log of both sides here. And on this side, the ln and the e are the inverses, and I just have k. So the natural log of base a gives me the constant that is the multiplier in the exponent of the e to the kt term. So let's take this natural log of 14.136218. The value you get if you plug that number in, hit the natural log button, you'll get 2.6487. So that this form can also be written as y equal to e to the 2.6487x. So there's several different ways you can work to go from one form to the other.